So hi everyone, I welcome you all to the seventh lecture of thermal properties of matter. So in the last class, uh, I introduced with the concept of radiation. So radiation is nothing but the mode of heat transfer that does not require any medium, and it's the EM wave. It is nothing but the EM wave. So according to then I discussed the Provost theory of exchange. So according to Provost theory of exchange, so there are some points that needs to be noted down based on the body. Maybe more or less that depends on the temperature, but there is a radiation at all the temperatures above absolute zero. Then the amount of thermal radiation per unit time depends on the nature of emitting surface area and temperature. That we know, we will see later also how these radiation formula are related to each other on these parameters. Body also absorbs the part of the thermal radiations emitted by the surrounding body. So if surrounding body is emitting some radiation, then body has ability to absorb that also. This radiation is different from what it is emitting by this. These radiations are coming from some different body outside that. Like you see sun and you are there on earth. So you are basically absorbing some amount of heat from sun. That is a sort of picture there. Then this theory also tells us that how the temperature of the body will change if it's if we compare the temperature of body with the temperature of surrounding. So if the temperature of body is greater than temperature of surrounding, then we know that emission is greater than absorption. And because emission is greater than absorption, then the temperature of body will get decreased, and due to which it gets cooled. However, vice versa is possible if the temperature of body is less than the temperature of surface of the surrounding. Like if we are on Earth and sun is radiating heat, then absorption is higher than emission, and due to which our body, if you see uh, in the summer days, many of the things that is exposed to sun radiations of sun becomes hotter, and so the same thing is according to this theory is that the temperature of body increases if the temperature of body is less than the temperature of surrounding. So that's all about the proposed theory of exchange. Then I introduced the concept of black body radiation. So black body radiation, so first we define what is black body. So a perfect black body is the one which absorbs all heat radiations of whatever wavelength. So lambda, I already told you that is wavelength incident on it. It neither reflects nor transmits any of the incident radiation, and therefore it appears to be black because there is no reflection and also no transmittivity. So it's a black body. So there is the example that is lamp black. Ferry's black body comes into the picture where he tried to make one of the body where it's a circle. So the radiation incident on it, and there is a multiple reflections occurred inside this body, such that this radiation will not come back out of this body to the surroundings again, and that's why it is called to be as Ferry's black body. Now I'm uh, introducing. I am telling you about the absorption, reflection, and so this is absorption, reflection, and absorption, reflection, and emission. So from these parameters, that is reflectivity, transmittivity, and absorptivity, we can characterize the material. So what I try to tell you here is like Q amount of heat is radiated from the surrounding, and it is absorbed by the surface. Let's say QA amount of heat is absorbed out of Q that is falling on the surface. QT amount of heat is transmitted, and QR amount of heat is reflected. So the total Q is has to be conserved. So that is equals to QR, that is reflected, QT that is transmitted, QA that is absorbed. And we get to know what is R, T, and A. So R is reflectivity, T is transmittivity, and A is absorptivity. So we can characterize the body, any body, based on the value of R, T, and A. So if it is, so there, as I introduced the concept of a black body. So if R is 0 and T is 0, so there is no radiation, there is no reflection, there is no transmittivity, and there is only absorptivity, that is equals to 1. So that is perfect black body. Second is if R is 1 and T is 0 and A is 0, that is a perfect reflector. So whatever the radiation comes, it gets reflected. If R is 0, T is 1 and A is 0, then it's perfect transmitter. There's some sort of a transparent, ideal transparent body where there is no reflection, none of the amount of heat is absorbed. Whatever you fall, whatever the heat falls on it, gas transmitted to it. So that is all about the reflectivity, transmittivity, and absorptivity. Now we'll look some of the terms, that is absorptive. First we'll look. So A is important here. So A is absorptivity. So that is amount of heat incident on body gets absorbed divided by the total amount of heat, total amount of heat incident on it, and that is Q absorbed divided by Q total. Okay. Then we have emissive power. So unlike reflectivity, transmittivity, and absorptivity, it is a dimensional quantity. And emissive power is the energy radiated per unit area per unit time. So that is emissive power. So it is defined as energy or heat radiated per unit area per unit time. We have another term that is spectral emissive power. So basically it relates that every temperature has a unique wavelength, then that unique wavelength has unique emissive power. And so that spectral emissive power can be related to the total emissive power like this. So that is 0 to infinity. E lambda into d lambda. And d by d lambda is equals to g lambda. So that is the E lambda is spectral emissive power. So it covers the whole range of spectrum. Okay. Another term is that is emissivity, that is E. So that is similar to, or so in emissivity we compare E comes out to be emissive power of a normal body divided by emissive power of black body for a given temperature, that is emissive power of a body at temperature T divided by emissive power of a black body at same temperature at same temperature. So when you need to compare the emissivity, when you want to compare a emissive power of a body with a black body, then this emissivity comes. Now let's look at the law, that is Kirchhoff's law. So in general, we know that good absorber absorber are good emitter. Means to say that if absorptivity is high, if A is high, then emissive power is also high, which means to say that E is directly proportional to emissive power. Sorry, emissive power is directly proportional to the absorptivity. So emissive power is directly proportional to the absorptivity. Also for spectral emissive power, so that is E lambda is directly proportional to A lambda. So Kirchhoff basically gives a relation that is E by A is for a particular body, let's say B, is equals to the E of black body. That's the Kirchhoff's law. We can feel it like you have a three bodies. So you have three bodies of same dimensions. So first point is dimensions are same. Another point is whatever the heat is coming. So whatever the heat is coming, that is coming at a heat falling on these bodies are of same wavelength and same temperature such that Q1 is equals to Q2 is equals to Q black body. So some heat is incident on it. That all is same. That is, let's say Q. Emissive power of this body, first one is not emissive power. The absorptivity of first is A1. The absorptivity of second body is A2. And this is AB, and that is one we know. We also know that emissive power is nothing but Q by A into delta T. Or we can say Q to be E A delta T. So for a particular delta T, so we have Q for all. Q is equals to E 1A delta T. Q is equals to 2A delta T. Is it correct? For black body, it's okay because A is 1, but this is not correct for this. That's the whole point of absorptivity comes when we say that. So A is absorptivity. Amount of heat absorbed divided by the total amount of heat radiated. So if you want to find the amount of heat absorbed, heat absorbed, that is into A into Q, that is there. And A into Q is nothing but equals to E A into delta T. That is also heat, and that is also a heat unit of heat. So that is for the case of no. So what I was said here is, so this is the emissive power of black body. If it is not a black body, then it will become E some body 1 A1 Q by A into delta T. Okay. So A1 Q is E1 A into delta T. From here, for in this context, A2Q is equals to E2 A into delta T, and Q is equals to EB A into delta T. If we divide 1, 2, if we divide 1 with 3 and 2 with 3, what we get is A1 by E1 is equals to A2 by E2 is equals to 1 by EB, or we can write it like, it's better to like BB because I'm saying black body or over. So E1 by A1 is equals to E2 by A2 is equals to EB. That is the Kirchhoff law. So the formal definition is the ratio of emissive power to the absorptive power for the radiation of a given wavelength is same for all the body and equal to the equals to the emissive power of a black body for same wavelength and temperature. So that is Kirchhoff's law. So there are two more laws that has to be discussed. So before going to that, let's look at one of the question. So the question is, so we have this plot is given. So that is temperature versus time, such that this is y, this is x. Options are Ex greater than Ey, Ex greater than Ay, Ex less than Ey, Ax less than Ay, Ex greater than Ey, Ax less than Ay, Ex less than Ey, Ax greater than Ay. So first point, one hint is that one thing is very clear that from the Kirchhoff law we know that emissivity is directly proportional to the absorptivity, because emissive power of black body is a constant. So whatever the sign we use for emissive power is equals will be the same for the absorptive power. So we can directly eliminate two of the options where the signs are opposite. So if Ex greater than Ey, Ex less than Vy. That is wrong. So that is not possible. And this is also not possible because the signs are opposite, and that is violating the Kirchhoff's law. Now the question is among A and B. So among A and B, we know we can compare E because we know that E is directly proportional to T to the power 4. That I saw, I'm sorry that I have not mentioned in the previous lecture or in the properties of the radiation. But emissive power is directly proportional to the temperature. Okay, sorry. So the temperature is not needed here. We need a dependence of time. So from here, from the above definition, that is delta T. We know that T is inversely proportional to delta T. And we know that from this Provost's theory of exchange, or from the general properties of radiation that I have discussed in the last lecture, that as the temperature increases, the radiation, the intensity of the radiation increases. Means to say that I already told you that E increases. So E increases with the temperature, and from where we get to know that E is directly proportional to T to the power 4. I will tell you about this from there is coming. But for now, for very vaguely, we know that if we don't know this relation also, that E increases with the as the temperature increases. So here, if you see for a particular set of time, let's say delta T, let's call it this. So the change in temperature, from here to here and from here to here, if you see, so the temperature change Ty is greater than Tx. Okay. Similarly, Ey should be greater than Ex, because emissive power increases with the temperature. More temperature change, there is more emissive power for a particular set of time. E is inversely proportional to time, that is for both the case. So this is nothing, this is not giving any information. So Ey is greater than Ex, so that is there. And we know that according to Kirchhoff law, Ay should be greater than Ex. Okay. So that the correct option is this. Now let's look at the Wien's displacement law. So if you plot intensity or the emissive power versus lambda for a black body, then it will come something like this. And the temperature is, so the emissive power is maximum for a particular lambda, and that we called as lambda max. And that is for the case of black body, for one of the black body. And that is at particular temperature, let's call it as T1. So that's the plot that will always come when you have a E versus lambda. Now, as you change the temperature, as you increase the temperature, what will happen? The slope displaced, this peak gets displaced, and what we get is this peak will get displaced, and we get another peak something like this, another peak something like this. So if you see the peak here is this one, here is this one, that is lambda max, if we call it as lambda max 1, this is lambda max 2, and this is lambda max 3, and it is happening because the temperature is increasing. So this one is T1, this is T2, this is T3, such that T3 is greater than T2 is greater than T1. So that's the Wayne's displacement law. So it is there, it states that the black body radiation, so it states that the black body radiation curves will peak at different wavelengths at different wavelengths that are inversely proportional to wavelengths that are inversely proportional to temperature, which means to say that lambda 1 or lambda max 1 into T1 is equals to lambda max 2 T2 is equals to lambda max 3 into T3. That relation is there such that lambda max is inversely proportional to temperature. So that's the Wayne's displacement law. Okay. And the area under this curve is, so area under this curve comes out to be area under curve is directly proportional to T to the power 4. And this area is nothing but E. So that E is directly proportional to T to the power 4. And so Q by A T is directly proportional to T to the power 4. So this area under the curve, under the black BB curve, is directly proportional to T to the power 4. And when Stephen came, and we called it as Stephen Boltzmann law, so where Q by A T is equals to nothing but sigma T to the power 4. So that is what is there for black body. For a general body, I will tell. So Q is nothing but sigma A T to the power 4. And the power comes out to be, so power of a black body is sigma A T to the power 4. Okay. And so that is for a black body. If you want for general body, for any body, then P is nothing but A E sigma A to the power 4. Sigma is the Stephen's constant. So E is emissivity. Sigma is Stephen Boltzmann constant. That depends on the property of a material. And for a general case, when there is a, so let's consider a case when there is a loss of power. So let's say this is a temperature T, surrounding temperature is Ts. So power loss, we need to find out power loss. So power radiated is E sigma A T to the power 4 power absorbed from the surrounding is E sigma A Ts to the power 4. The power loss is PR PA. So that is PR minus PA. So that is E sigma Both the processes are happening to the same body, so sigma and E should be same and the area should be same, and the temperature is difference is there. A into T to the power 4 minus T naught. So that is TB to the power 4 minus T naught to the power 4. So in a formal way, I can write Stephen Boltzmann law, and that's the last part of this thermal properties of matter. So the total energy emitted, radiated per unit surface area of a black body across all wavelength per unit time is directly proportional to the fourth power of the fourth power of the black body's thermodynamic temperature. Okay, so that is the Stephen Boltzmann law. And keep this in mind while putting this temperature. Check the unit of the temperature. If the sigma is given in, mostly it is given in Kelvin. So don't put this in degree centigrade. That's the usual mistake that anyone do. So I'm taking one question and we'll end up with this thermal properties of matter. So we have two black bodies. That is JE question, I guess 2015. And this is another black body, that is B. Such that RA, radius of A, is 400 times the radius of B. Power emitted by A is 10 to the power 4 of B. Find, we need to find lambda A by lambda B. Options are A 7, B 4, C 3, D 2. So that is a bit easy question that covers all the concepts of all the laws mostly that we have covered. So when we need to find out lambda A by lambda B, so lambda A by lambda B, we need to know. So we know that according to Wayne's displacement law, lambda A TA is equals to lambda B TB. So lambda A by lambda B is nothing but TB by TA. So that is the first relation. Another relation we know, that is power. So power of A by power of B is equals to sigma A, sigma 1 A1. It's a black body, so E is 1. A to the power TA to the power of 4 divided by sigma 2 A2 TB to the power 4. Sigma is given to be, so the property sigma A is given sigma B because it is given both are of same material. So both of them are of same material. So sigma 1 is equal to sigma 2. So PA by PB we know that is 10 to the power 4. A1 by A2. So A is directly proportional to R square. So R, sorry, it's not A1, it's A and B. That is RA square by RB square into TA to the power 4 divided by TB to the power 4. 10 to the power 4 is equals to We know RA by RB. So RA by RB is 400. So 400 square into TA by TB to the power 4. So we need to find to get this lambda A and lambda B from this relation TB by T or TA by TB. So TA by TB comes out to be 400 to the power 1 by 2 is equals to 10 to the power 4 to the power 1 by 4, and TA by TB into 20 is 10. So TA by TB comes out to be 1 by 2. So now we know TA by TB to be 1 by 2. So TA by TB is lambda B by lambda A. So lambda B by lambda A is 1 by 2, and so lambda A by lambda B is 2. Okay, so that is the correct option. So I'm giving you one question, just some theoretical type of question. Try it at home. So you have a black body. That's a simple question. Area is 10 centimeter square. Temperature of surrounding is 27 degrees centigrade. Temperature of black body is 227 degrees centigrade. Sigma is given to be 6 into 10 to the power minus 8 volt per meter square, Kelvin to the power 4. You need to find what is rate of power loss. Just try it at home, and that's a simple question. Just only thing is that put temperature to be in Kelvin. Okay, thank you.